All right, so far what we have discussed is a homogeneous equilibria, and I call it homogeneous because the phase of all the components of the reactants as well as products is the same, but not all reactions would be such where every single reactant and every single product is going to be in the same phase. It's a possibility that your reactants are perhaps gaseous and they give you a solid product, or you begin with a solid and maybe you heat it and the products are gaseous in nature. Such kind of reactions in which the phases kind of differ, they're all across the board, solids, liquids, or gases. We use the word heterogeneously equilibria for those. So heterogeneous equilibria are those in which reactants and products, they are basically present in more than one phase. Just, to give you a flavor, if you have, let's say, ammonium carbonate and you heat it, all right, and it goes through decomposition, so it gives you ammonia, and I should probably not have that. It gives you ammonia, and it will give you water, and it'll give you CO2. So all the three are gaseous in nature, whereas your starting material was a solid. So this will be an example of heterogeneous equilibria. You can consider carbon monoxide, which is in the gas form, to be in equilibrium with CO2, which is a gas, and carbon, which is a solid. So in this case, you might expect that your equilibrium expression, the K, according to the law of mass action, should look like, if it's a balanced equation, it should look like CO2 times carbon divided by carbon monoxide, and you take a square of that. But since carbon is a solid, its concentration is constant. That means that if you double the amount of carbon, the concentration remains the same. The concentration of a solid does not change because a solid doesn't expand to fill its container. So the volume doesn't get affected. Its concentration therefore depends only on the density. And since density is an intensive property, it remains constant as long as some amount of solid is present. We would say that the amount doesn't change, and for that reason, whenever you have pure solids or pure liquids, those are not going to be counted in your equilibrium constant. So the correct equilibrium expression would be the one that does not contain carbon, and so Kc in this case would actually be concentration of CO2 divided by concentration of carbon monoxide, and we'll take a square of that. Now, similarly, recall I told you that concentration of a pure liquid does not change either. So if you have a pure liquid, reactants or products labeled in the chemical equation as an L, those are also excluded from the equilibrium expression. So if you had something like perhaps CO2, which is a gas, you're treating it with water, which is a liquid, and that gives you H plus, that's AQ, plus carbonate, which is also AQ, or bicarbonate rather, with one negative, so H2CO3. Since H2O is pure liquid, that's not going to feature in our equilibrium expression. All right, the question this hour is, for each of the following reactions, write the equilibrium constant expression. We are writing Kc. So how would we go about it? Realize, again, solids and liquids will not feature. So the first one, Kc, should look like, any ideas? Should that Fe2O3 be used in the expression? The answer to that is no. So you take hydrogen gas, take a cube of that, you take water, you take a cube of that as well. Of course, the first step would have been to balance the equation, but I know in this case I took the time to balance them. But if this was a test question, I would very strongly recommend that you should balance the equation and check for, just verify before you start writing the KC, just in case. Likewise, KC for the second one, hydrogen gas, square of that, concentration of oxygen. We do not count water because that's in the liquid phase. Third KC, SI won't count, and so it will look like HCl raised to the power of 4, SiCl4 times H2 square of that. Last one, Ag2Cl2 is a solid, it won't count. What do you put in? 1 as the numerator, not 0, 1. And then Ag2 plus times Cl negative square of that. These should be your equilibrium constant expressions for the Kc. All right, the next question is, which of the following has a heterogeneous equilibria? So what you're seeing, what you're looking for is these phases. These should be different. So since all three are gases, you would say this is homogeneous. Again, all are gases, you say these are homogeneous. Gas, gas, solid, gas, this is heterogeneous. Okay, let's then discuss equilibrium constant, what the value suggests. We have briefly taken a look at that, but we are going to take a look kind of from the perspective of instantaneous rate and average rate. Remember that from chemical kinetics. We are going to take a look at what is called as the reaction quotient and equilibrium constant. So again, one more time, what does equilibrium constant really tell you? Equilibrium constant helps you in judging the extent of reaction. Greater is the number, and you can safely predict that more of the products are going to get generated. Smaller is the number, that means the backward reaction has triggered off, and that would mean that your reactants will be the major component in your equilibrium mixture. So you can very safely predict the direction of the reaction as forward or backward. You can do that if you know the equilibrium constant value. And of course, you can calculate the equilibrium concentrations from any equilibrium, any initial concentration that is provided to you. So we are going to take a look at that as well. Now, like I was saying, if the value of Kc is more than 1,000, that's when you would say that that's a fairly large value, and it's primarily your products that are going to be in your equilibrium mixture. On the other hand, if that value is less than 10 to the power of minus 3, then you can say that it's a fairly small value, and so it'll be primarily reactants. The left-hand side will be more predominant, and any value in between, that would mean it's kind of like a 50-50 or more like 40-60 type of a ratio. And so you would be able to say that both reactants as well as products are going to stay in that reaction mix. This information is very pertinent for your upcoming dry lab 2. So again, K value higher than 1,000, primarily products, K value less than 0.001, primarily reactants. Any value in between, like 98 or 0.98, would mean you have appreciable amounts of both reactants as well as products. All right. Let's then talk about reaction quotient and what that is. Okay, so reaction quotient, basically denoted by QC, is not equilibrium concentrations, but any time other than that. What I mean by that is, when consider a situation when reactants of a chemical reaction mix and they are bouncing around and they react with each other, they generally react to form the products. That's the end game. We say that the reaction proceeds to the right-hand side. We say that the products are being formed. And the amount of the product formed, the extent of the reaction is going to be dependent on the magnitude of the equilibrium constant. We have seen that larger the value, if that value is more than 1,000, you would say that the direction of the reaction is going in the forward direction towards the products. However, what if you haven't quite reached the equilibrium and your mixture contains both reactants as well as products, both of those? Can you still predict the direction of the reaction? So for example, at any instant on your, remember that reaction profile where you had the concentration and you had the time? So you haven't hit this constant, this region of constancy where the concentration doesn't change, because that's the region where equilibrium has been hit. But any other time, any of those times, how can you figure out whether the reaction is still going in the forward direction or whether it's going in the backward direction? In order to figure that out, in order to compare the progress of the reaction to the equilibrium state, we use a quantity called as reaction quotient. So in that sense, you can consider reaction quotient to be similar to instantaneous rate, because it is not sort of the average of the reaction, but rather at any one particular instant of time. Of course, as the time passes, the QC, or the reaction quotient, is going to tend to the equilibrium constant value. And of course, once it hits the equilibrium, then QC becomes equal to KC. So what you can do is you can determine the reaction quotient at any given point of time. If that value is less than the equilibrium constant, you would say that the reactants still have an opportunity to go to the products. So it's moving in the forward direction. On the other hand, if your QC becomes, if your reaction quotient becomes more than the equilibrium constant, then it's the backward reaction which has triggered off. So products are getting converted into the reactants. And on the other hand, if the two are exactly equal, you say that no net reaction takes place, or we have basically hit the equilibrium. So just to kind of give you a flavor for this, let's say we have a general reaction. A moles of A react with B moles of B, giving you C moles of C and D moles of D. And if you have to define the reaction quotient QC at any given point of time, you would say that it is going to be the concentration of the products raised to the power of their stoichiometric coefficients times the other product raised to the power of its stoichiometric coefficient, divided by the reactants times B raised to the power of B. And likewise, you can write down a QP, which will be PC to the power of C, PD to the power of D, PA to the power of A, PB to the power of B. And so in that sense, you can say that the difference between reaction quotient and equilibrium constant is just this, that at a given temperature, equilibrium constant has only one value, because this is the time when your curve has basically hit that constant mark. So the equilibrium constant will have only one specific value at a specific temperature, and we would say that it has hit equilibrium. The reaction quotient, however, depends on the current state of the reaction, so it can have many different values. For example, in the reaction mixture containing only reactants, the reaction quotient is going to be 0. Why? Because the reaction has just started, and so the concentration of products has not quite built up yet, and so the numerator here is 0. So you would say QC is 0 at the beginning of the reaction. On the other hand, once your reaction is completely done, now if you contain only products, then the QC would be equal to infinite, because you're going to end up with no reactants in the reaction, and so the denominator is going to be 0 in that sense. So in a reaction contain mixture which contains both reactants and products, and let's say each is at 1 molar concentration, you would say that QC in that case is going to end up being 1. So really realize that reaction quotient, the way it's calculated, is nothing different than the way you calculate the equilibrium constant K. But equilibrium constant is something that you hit. It has one fixed value at a specific temperature. That is the horizontal part, the plateauing out of the curve. Whereas the reaction quotient could be at any of these points. It's going to change throughout. And again, one can say that if Q is less than K, that means the reactants are getting converted to products. On the other hand, if Q is more than K, that would mean that a backward reaction, products are getting converted to reactants. And if Q is equal to K, then that would mean that we have hit the equilibrium. So reactants and products are in equilibrium with respect to each other. Let's see if we can actually apply this to a real problem. The question here is, the equilibrium constant for the reaction 2NO plus O2 giving you 2NO2 is 6.9 times 10 to the 5th at 500 Kelvin. So they've given you the value of K. A 5-liter vessel at this temperature, was filled with 0.06 moles of NO, 1 mole of oxygen, and 0.8 moles of NO2. The question is the reaction mixture at equilibrium? And if not, in which direction does the net reaction proceed? Realize two things. The first thing is you can predict the direction, what we discussed earlier. You can say whether you'll have more products or more reactants. You can tell that on the basis of the value of equilibrium constant, right? But there's another way that you can do that, and that is using the value of reaction quotient. So is there one method that you can convert these moles into concentration and be able to use the law of mass action? And hopefully you can see what I'm talking about. Kc, or Qc rather, is going to be equal to NO2 square divided by NO squared times O2. NO2 is going to be 0.8 divided by 5 whole square, 0.06 square of that, 1 mole of oxygen. Of course, we have the 5 each time. And we are going to solve this. So this comes out to be 0.16. We are taking square of that, and then 0.012. We'll take a square of that as well, and that will be 0.2. So let's work out the math, and then we'll divide that by 2. It gives me 888.888. So this is my reaction quotient, Q. And now I'm going to compare that to the value of K at the same temperature. And since the value of K is much larger for this one, we can say that Q is smaller than K. That basically means that it's not equal to K, which means it's not at equilibrium, and we say that it's the forward reaction that is proceeding right now. The second part is, what is the direction of the net reaction if the initial amounts are 5 times 10 to the negative 3 for NO, 0.2 moles of O2, and 4 moles of N2. So we are going to do the same thing again, calculate Q and then compare that to the value of K. But now you would be plugging in different numbers here. Realize we are again using the volume, so moles divided by volume gives you molarity. That's the molar concentration. That's what I'm going to go with right now also. So 4 divided by 5, square of that, and we are going to divide that by 0.005 divided by 5, square of that, and 0.2. And let's work it out. And in the second case, the value comes out to be much different. It comes out to be 3.2 times 10 to the power of 6. That number is larger than the value of K. So in this case, since Q is more than K, it's greater than K, it's a backward reaction that is proceeding. So this is an application. Anytime Q less than K, it's a forward reaction towards the products. Anytime Q is more than K, it's a backward reaction towards the reactants. Anytime it is exactly equal to K at a certain temperature, you say equilibrium has been hit. Okay, I want to spend a couple minutes in going over certain kinds of questions. So let's say I have a reaction to COF2. It's in the gas phase and it's getting converted to CO2, which is also in the gas phase, CF4, gaseous, and the Kc is given to be 2 at 1,000 degrees Celsius. And in the equilibrium mixture, the concentration of COF2 is supposed to be 0.255 molar. The concentration of CF4 is 0.118 molar, and they're asking what is the concentration of CO2. So that's, pretty straightforward actually if you think about it. You have been given a certain amount of information and you have been asked to determine the concentration of CO2. Everything is at equilibrium. So you should plan this using the definition of equilibrium constant, since that is going to be equal to concentration of CO2 divided by CF4, times CF4 divided by COF2, square of that. All of 3 of these are gaseous, so all 3 of them are going to count. And the value of this equilibrium constant is given to be 2. So you would say, now start plugging in the numbers. CO2 times 0.118 divided by 0.255, square of that is equal to 2, or CO2. We are going to solve for CO2. That means I'm going to multiply both the sides of the equation by 0.255, square of that, and I'm going to divide both the sides of the equation by 0.118. So 2 times 0.255 square, 0.118, and we'll solve this. On my calculator, I'm getting a value of 1.10, and since it's a molar concentration, we'll say it's molar, and that's it. What's trickier is to determine the equilibrium concentrations when we know the equilibrium constant and the initial concentrations. So usually the example that I just showed you, we would have the equilibrium constant and we were basically figuring out the concentration of one of the components provided others were known. So it was kind of like a plug and chug type of a situation. On the other hand, what we are about to go over, it's more intricate, it's more delicate. We need to find out the equilibrium concentrations of reactants and products, and these will be more involved, like I said. And there's a specific procedure that is required to be followed. And we are going to do this for a long period of time, though, so the earlier we start, the better it is. So what we have is, let's say, a general reaction, a generic reaction. Some A gas is getting converted to another B gas. Okay, now if we say that in the reaction mixture, the initial concentration of A is, let's say, 1 molar, okay, and B is at 0 moles or 0 molar. And we have some idea about the equilibrium constant. We know that the equilibrium constant is maybe 0.33, and I'm just coming up with some random number, all right? And we want to find out the equilibrium concentrations of A and B. How would we go about it? Now, let's say that as the reaction occurs and a change has taken place, so the change that takes place with respect to A, let's say that is by x moles. So you can say that for every x moles of A that is used, that means there should be a negative sign, there will be 2 x moles of B that will get generated, right? One more time. So since I know nothing about what goes on at equilibrium, I'm just going with the change that occurs in the concentration of A as well as B. And since the stoichiometry of the reaction describes that for every mole of A that reacts, 2 moles of B should get formed. I used that to figure out the negative x representing the moles of x that would have reacted, and 2x representing the B that got formed. So at equilibrium, what happens? Turns out what happens at equilibrium is the sum of the entries above it in the ice table. So 1 plus minus x and 0 plus 2x is what you have. So you would say that equilibrium constant, which by the way could be written as b square over a in this case, is nothing but 2x square of that divided by 1 minus x, and that value is equal to 0.33, or you can simplify that as 4x square 1 minus x is equal to 0.33. Now this starts to look like a quadratic equation because it contains the variable x that has been raised to the second power. And in general, if you were to solve the quadratic formula, you would solve using the b square or minus b plus minus square root of b square minus 4ac divided by 2c. So you would use that formula to determine the values of x. And we are going to do it both ways. I'm going to show you the solution of a quadratic equation, and I'm also going to do the assumption, the approximation that we can use, which makes the calculation a lot easier. So let's see if we can actually apply the quadratic here. This should look like 4x square plus 0.33x minus 0.33 is equal to 0. And my general solutions for quadratic equations are that if you have an equation which looks like ax square plus bx plus c equals 0, then x has two solutions, minus b plus minus square root of b square minus 4ac divided by 2a. Realize out of these solutions, only one is usable because after all, what is x? X is a concentration, and that can never be negative. So the one solution that you will get by the combination of minus b and the minus square root of b square, you can simply just omit it out because a negative number has no meaning as far as concentration goes. But you will still have to solve the other one. So in this case, x will start looking like minus 0.33 plus minus square of 0.33 square minus 4 times 4 times 0.33 divided by 2 times 4, that's 8. Now, I'm not going to actually complete this calculation because I just came up with some numbers and it's a possibility that we might actually have some irrational numbers here. But you get the idea that solving a quadratic means you will have to plug this value in. And so be ready. There could be like one problem perhaps in the dry lab where you might have to plug in and solve a quadratic equation. Let's, for the sake of argument, let's work on some real numbers, some experimental numbers. The reaction in question is N2 plus O2. Both of these are in gaseous form, and they give you 2NO. Okay, and the Kc is given to be 0.1 at 2000 degrees Celsius, and the reaction mixture initially contained, so the initial for the I, and by the way, these are called as ICE problems. So for N2 I have 0.200. For oxygen also I have 0.200, and of course I will have no concentration of the product in the beginning. And let's say X moles of N2 react with X of oxygen. 2X of NO will get formed. That would mean you have equilibrium concentrations that look like this. And now we are going to substitute those into the equilibrium constant expression, which will look like NO squared divided by N2 times O2, which is 2x square of that, 0.2 minus x, and it is really 0.200. 0.2 minus x is equal to 0.1. And now we are going to, let's just write that so we don't forget the sig figs. And now we are going to solve that. Okay, so we have, hopefully we can write it as 2x 0.200 minus x squared is equal to 0.1. Or you can perhaps even say that 2x divided by 0.200 minus x whole squared is equal to 0.1. So if you take square root of both sides, you would be able to say that 2x, let's just write it on another page, 2x divided by 0.200 minus x is equal to square root of 0.1, which came out to be 0.316. And now we simply just solve for x. Actually, we made life simple for ourselves because it's no longer a quadratic. So sometimes you might be able to, get benefit depending upon how the concentrations look like. So this will be 0.0632 minus 0.316x, and so that will come out to be 0.027. So if x is the amount that reacted, then at equilibrium nitrogen was supposed to be 0.200 minus 0.027, which will be 0.173 molar. Oxygen will be the same thing, and NO is supposed to be 2x. So 2 times 0.027, which comes out to be 0.54, 054 rather, molar. And you can check your answer if you want to by substituting the computed equilibrium value into the equilibrium expression and see what you get. And in this case, if you do that, you would say 0.054 Square of that divided by 0.173 divided by 0.173. That value on my calculator comes out to be 0.097. Whoa, it's an equilibrium constant, so no units. And the value, recall, that we were given was 0.1. So it's pretty close. And so the answer that we got is valid.